So in section 11-3, we're going to be talking about infinite geometric series, and we're going to start off with this sum. And what you'll notice is it's geometric because I'm multiplying by 1/2 to get from one term to the next. So I keep multiplying by 1/2 to get to the next term, and so on. So the other thing that makes this infinite is the dot dot dot. I'm not going to add like 10 terms or 12 terms. I'm going to add an infinite amount of terms. And I want to see what the sum is approaching. So what I'm going to do is use the calculator to help me out. So what I've done is I've found the sum of the first 10 terms right here. And then, so if I were to continue this out for 10 terms, the sum would be 0.999023. And then what I've done next is I found the sum of the first 30 terms. So continuing this out for 30 terms, adding them all together, what I end up getting is 0.99999999068. So it's getting really, really close to what it's looking like when I go ahead and sum up the first 100 terms. I end up getting the calculator's answer as 1. So what's happening is that this sum is approaching 1, and it's not going to go over 1 because notice what's happening with the numbers. The next one will be 1 over 64, and the fractions are getting super, super small, so what's ended up happening is I'm not really adding much to my decimal. So I end up eventually just adding nothing or something so small it doesn't have a significant effect on the sum. So the sum, it looks like it's approaching as 1. So what we're going to be doing is coming up with formulas to find the sum of an infinite geometric series. And it all depends on the common ratio, R. We don't want to have to add up, 100 or 1,000 to kind of figure out what the terms are approaching. So there's got to be a formula to just tell us what the sum is approaching, and here's what it is. So case 1 is if the absolute value of your common ratio, so remember this is the common ratio, if the absolute value of it is less than 1, then here's how you find the sum. You take your first term, so this is your first term, and your common ratio, and you do the first term over 1 minus your common ratio. That tells you what the sum is. So let's go back to that example that I gave a few minutes ago, the 1/2 plus the 1/4 plus the 1/8, where I ended up finding the sum of the first 30, then the first 10, 30, and 100 terms, and I found out that the sum was approaching 1. Well, now if I look at the common ratio is 1/2 because that's what I'm doing to get from one term to the next as I'm multiplying by 1/2. And so since the absolute value of 1/2 is less than 1, so I'm using this right here, I know that I'm going to use this formula. So the sum would equal the first term, which is 1/2, over 1 minus the common ratio, which is 1/2. Well, basically I get 1/2 over 1/2, or 1, and that's what I got on the calculator by just summing up a whole bunch of terms. So that brings us to case 2. What if your common ratio is bigger than or equal to 1? Then your sum is either going to be infinity or negative infinity, and it all depends on your first term. It's infinity if your first term is positive, and it's negative infinity if your first term is negative. So here's an infinite geometric series, infinite from the dot dot dot, geometric because I'm multiplying by 3, and I had put an 8 in there. It wasn't supposed to be there, so when I multiply 6 by 3, I get 18, and then 18 by 3, I get 54. So this is geometric where R is equal to 3. So notice that this is bigger than or equal to 1. So I know my answer, these are going to be infinity or negative infinity. Well, if you just kind of look at this sequence, if I add 2 plus 6 plus 18 plus 54, the numbers are getting they're getting larger, so the sum is going to get larger. And since the first term is positive, that means the sum is going to be infinite. If I were to keep adding more and more terms, the sum would just get bigger. Alright, and here's the last case. So you have an infinite geometric series, and what if your common ratio is less than or equal to negative 1? What ends up happening is no sum exists. So here's an example. So I have a sequence 3, then negative 6. So it looks like I'm multiplying by a negative 2 to get from one term to the next. So I'm multiplying by negative 2. So negative 2, so since r is equal to negative 2, negative 2 is less than or equal to negative 1. It's smaller. So what happens, what this means, is no sum exists. And I'm going to show you why. So I'm going to start by adding the first two, the 3 minus the 6, so these two. If I were to add those together, I would end up getting negative 3. So then I'm going to go ahead and add the next term, 12. So when I add the next term, I end up getting 9. So then I'm going to add the next term, which is negative 24. So then my sum ends up being negative 15. Then I'm going to add the next term, and I'm going to add 48. So my new sum is going to now be positive 33. What ends up happening is my first sum was negative 3, then my second sum was 9, and then my next sum was negative 15. What's happening is I'm not approaching a single number. I'm going from negative to positive to negative to positive. It's not approaching one number. So what happens is that the sum does not exist. So I'm going to show you what ends up happening by adding the first two terms together. If I do 3 minus 6, I end up getting negative 3. And then I'm going to add the next term, which is 12. When I add the next term, I end up getting negative 9. Going to the next term, which is positive 9. I'm going to add negative 24. And I end up getting negative 15. Then I add the next term, which is 48. I end up getting a sum of 33. Let me backtrack and show you what happened. The first sum was negative 3. Then when I added the next term, I got positive 9. Added the next term, it went negative again. Added the next term, it went positive. What's happening is these sums are going from negative to positive, so it's never approaching a single value, so the sum does not exist. So now here's a series, and you're asked to find the sum. And so what you're going to have to do is find the common ratio. So what are you doing to get from one term to the next? And it looks like we're multiplying by a negative 0.2. So if I multiply this by a negative 0.2, I end up getting positive 0.04, and so on. So r is equal to negative 0.2. So what that means is we're going to try case 1. Is the absolute value of negative 0.2 less than 1? If it is, we're going to use this sum formula, first term over 1 minus r. Well, the absolute value of negative 0.2 is just 0.2, and that's less than 1. So yes, we're going to use this right here. So we're going to take our first term, which is 1, and then we're going to do 1 minus the common ratio, and the common ratio is a negative 0.2. So I end up getting 1 over, and this ends up being plus a 1.2. So when I simplify that, I end up getting 0.83 repeating, and that would be what my sum would be approaching. So I had to find the common ratio first, and then I had to plug it in to see if I could use this formula right here by seeing if the absolute value of that was less than 1. If it is not, I can't use that formula. So for this one, to get from one term to the next, it looks like I'm multiplying by 1.1. Because negative 1 times 1.1 is negative 1.1. When I multiply 1.1 by negative 1.1, I end up getting negative 1.21. So it looks like the common ratio is 1.1. So is the absolute value of 1.1 less than 1? If so, I'm going to use the formula that I used before, a1 over 1 minus r. Well, this is not true, so I'm not going to use that formula. So I go to the second case, case 2. Is r bigger than or equal to 1? Absolutely. So when this was the case, then that means the sum is either infinity or the sum is negative infinity. You have to pick. Well, look at the terms. When I add them together, they're becoming more and more negative. So that means the sum is negative infinity. So I want to point out on the handout that you picked up in class today, this is what you just took notes on. So you have all of the sums of the infinite geometric series where you can find out what the sums are right here. So now turn it over to the backside. So on the backside you're going to see Pascal's triangle, and one of the things that's significant about the triangle is that if you add the two numbers above, it's the number below. So like 4 and 6 add to 10. 15 and 20 add to 35. 4 and 1 add to 5, and so on. So basically what we have is we have a whole bunch of rows. So this right here would be row 0. This right here is row number 1. This right here is row number 2. Basically what you can do, this is row 3, is if you look at the number right here, this tells you the row it is. So you see how row 3 has a 3 right next to the 1, and then row 2 has a row 2. So this right here would be actually row 10. And if you want to put all the rows on there, that's fine. So you can actually use some probability combinations to calculate the rows of Pascal's triangle. So right here, this is row 8. So I'll put row 8. And I'm going to show you with the calculator using combinations how you can generate that. So what I've done is I've done 8C0. Notice how I get the 1. That's this guy right here. Then I do 8C1. I get the 8. That's the next term. 8C2 is 28. Next term. 8C3 is that. 8C4, 8C5, 8C6, 8C7, and last but not least, 8C8. So basically I can get any row of Pascal's triangle by using combinations. So if I wanted row 4, what I would do is 4C0, 4C1, 4C2, all the way to 4C4, which would be this term right here. 4C0, choose 0 is always the ones here. So that would be 2C0. This would be 3C0. That would be 5C0 because it's row 5. So you can get any row that you wanted. So if you wanted row 25, you do 25C0 all the way to 25C25. So this brings us to the binomial theorem, how we can expand a binomial to some power without having to do FOIL that many times. So these right here, the NC0, NC1, NC2, all the way to NCN, that all comes from Pascal's triangle. So those are going to be all the coefficients. So for example, if this was like a 3, then that would be 3C0, 3C1, 3C2, and so on. The other thing that you're going to notice is the exponents decrease by 1 each time till you get to 0. And then on the y's, they start increasing by 1 until they get to whatever this power is. So I'm going to go ahead and give you an example. So what you're going to do is you do not want to do this. You don't want to do 2x minus 1 and FOIL it out 4 times. That would be a pain. So I'm showing you a shortcut way. So what you're going to do is look at row 4 of Pascal's triangle. So row 4, the coefficients are 1, 4, 6, 4, 1. So you're going to write out 1, 4, 6, 4, 1. So what we've just done is we've just gotten all of our coefficients right here. Alright? So the next thing we're going to do is we're going to figure out the two things we're expanding. This is the x and this is the y in the formula. So you're expanding a 2x and a negative 1. That would be your x and your y basically. So the two things, you're going to copy them down next to each of them. So 2x, that should be a negative 1. And last but not least, the 2x and a negative 1. So what you're going to do is you're going to put pluses in between all of these terms. Okay, and then you're ready to put your powers. So the x term, the first term, this term right here, starts off at whatever you're raising it to. So since it's to the 4th power, I'm going to start the 2x to the 4, then it's going to decrease by 1 each time until it gets to 0. The y starts at 0 and then increases. So the y happens to be a negative 1, so it's going to start at 0, 1, 2, 3, and end at whatever the power is at n. So n is 4. So now we're going to simplify. Anything to the 0 cancels out. It's a 1. So that's out of there. So now, here's what you're going to do. You're going to raise 2 to the 4th and x to the 4th and multiply it by 1. So 2 to the 4th ends up being 16, and then we're going to multiply that by 1, so we just get 16x to the 4th. Alright, now you're going to do the numbers first. So you're going to multiply exponents first, so you get 2 cubed, which is 8, times a 4, which ends up being 32, and then we're going to multiply 32 by the negative 1, so we end up getting negative 32, and then I have this x cubed. Alright, going on to the next one. Do powers first. So 2 squared is 4, and then negative 1 squared is 1, so I get 4 times 1 times this 6. So I end up getting a positive 24, and then now I can do the x's, so I get x squared. Here I end up getting a 2 to the first times a negative 1 cubed. Well, negative 1 cubed is negative 1 times that 2 is negative 2, and then times that 4, which is negative 8. And then I get x to the first. And last but not least, a negative 1 to the fourth times a 1 is a positive 1, so I get plus 1. So here's your final answer expanded. So if you were to do FOIL for this, you would end up getting this if you did it correctly. This is just a shortcut way of doing it. Okay, so here's one last example. I'm actually not going to do this one with you guys. I want you to try it on your own, and I want to see if you can get it. I'll be checking it tomorrow, and we'll go over it tomorrow in class. Alright, that's it. I have a great evening.